Goldbach's conjecture using Bertrand's postulate. For those that don't know, that aren't familiar with Goldbach's conjecture, it is one of mathematics' oldest unsolved problems, dating back to 1742, and it asserts that all even numbers greater than 2 can be written as the sum of 2 primes. It has been proven computationally up to 4 times 10 to the 18th, which is a very large number, but no theoretical proof has been given just yet. However, Bertrand's postulate can be used to reveal a pattern among the prime numbers, which can be used to open the door to proving Goldbach's conjecture. Bertrand's postulate states that there is always at least one prime between x and 2x for all x greater than or equal to 2, where x is an integer. Therefore, for example, if you say x equals 2, then between 2 and 4 you've got 3, and if x equals 10, then between 10 and 20 you have 11, 13, 17, and 19 as the primes that are in that range. And so it's proven to be a fact that between x, 2x greater than or equal to 2, there's always at least one prime. So therefore, by induction, there will always be at least one prime between 2x and 4x. And if we take these two Bertrand frames, as I call them, or windows, and line them on the number line for different values of x, we see that a pattern starts to emerge. And that it appears that there are always 2 primes equidistant from 2x. And this pattern is also evident if we restate Bertrand's postulate to accommodate odd midpoints by saying there's always at least one prime between the floor of x over 2 and x, instead of saying between x and 2x. We just divide both of them by 2 and then take the floor, which just means to round down. For those that aren't mathematicians. So this is the basic structure of my conjecture, and my conjecture that if we take all the primes pi on the range the floor of x over 2 to x, and apply the formula qi equals 2x minus pi, then at least one qi will be prime. And I'll say that, but there are two anomalous values in which this doesn't hold exactly as I state, but I'll explain those in just a second, and you'll see that it still holds the claim of the prime symmetry still holds true, and still supports my claim of proving Goldbach. So when x equals 19 and x equals 43, this diagram shows when x equals 19, and if you take x equals 19 in the middle, and you take x divided by 2, you take the floor of it, you get 9. And if you look, none of the primes in between 9 and 19 reflect across to primes between 19 and 29. But if you relax Goldbach or Bertrand's postulate just a little bit to include, to not just say primes in between x over 2 and x, but to include the primes all the way back to 3, we'll see that we get one prime pair to match in 7 and 31, and 7 and 31 sum up to 2 times 19, which I'll get to that a little bit further as we go along. And here's the second example where the Bertrand windows don't work exactly as I prescribe them. So here's where the Bertrand window should be. And as you can see, there are no primes that correspond to these primes within the Bertrand window on the left. But if you if you relax Bertrand just to include all the primes all the way back to 3, then we get 4 prime pairs that match equidistant from or symmetric and equidistant from x in the middle, when x equals 43. And these are the only two examples that I've found all the way up to 5 million, to where the Bertrand window does not work. So if the Bertrand windows always contain equidistant primes other than the two anomalous values which I showed you, this implies that Goldbach's conjecture is true. If we always have two primes P and Q equidistant from any x greater than or equal to 4, we have P equals x minus D and P equals x plus, or Q equals x plus D. And then therefore P plus Q equals 2x because the D's cancel out when you sum them together. Therefore, every even number 2x greater than or equal to 8 can be written as the sum of two primes equidistant from x. And here are two examples of the pattern working exactly as it should. The first one is x equals 30, and in this example, this is very exemplary of the pattern, and then it's very unique in that all 4 primes within the left window correspond to 4 primes on the right window, and we got twin primes, cousin primes, sexy primes, and another pair of twin primes, all matching up in this pattern. And in the second example, I wish I could get rid of the taskbar, but I don't know how. But if you can see in this bottom example, the midpoint is x equals 68, and I just chose that at random. That was my football number from high school, and so just to throw out a random number that was in a manageable range so that I could display it on the screen. But so the two primes that match up on here just so happen to be sexy primes on both sides, which is pretty unique in that in my research you don't see that like this one in x equals 30, you got twin, cousin, and sexy primes matching up, and then this one, the only two that match up are sexy primes, which I'm not being dirty about saying sexy primes. Sexy primes are primes that are separated by a distance of 6. And this example, this is a full number line of the year, the days of the year. And I included because it's my birthday is the midpoint of the year, which is July 2nd. And I was born in 1986, and in 1986, July 2nd was a Wednesday. So I was born middle of the year, middle of the week, and I was born around midday. And I'm also a middle child. And so it was just kind of providence that I discovered this pattern of symmetry. And as you can see in this example, if you look back in the Bertrand window to the left, there are primes that match up in the Bertrand window on the right, and then there are primes on the outskirts that match up on the outskirts on the right. And then here's a probabilistic argument for why it should hold for large values of x. So by the prime number theorem, the prime counting function pi of x gives you the number of primes up to x. And so the number of primes on the interval x over 2 to x is approximately x over 2 times the natural log of x. And then the probability that a given q that is near x is prime is 1 over the natural log of x. And this is all by theorem. And then using the Poisson distribution, because n is large and p is small, we can use np as the Poisson parameter, and they're using the probability that k is equal to 0 in the Poisson distribution. We can see that the probability that at least one q is prime increases and approaches 1 as x grows large. And I did examples where x equals 20, 100, 200, 500, 1,000, and 2,000. And as you can see with the Poisson distribution, the probability that at least one q is prime approaches 1. Now this example is a cheat sheet to find, to weed out non-primes in the search for Q values. The way this chart works is you take X and P and D, where P is your given prime that is a distance D away from X, the midpoint, and you take them all mod 12, which divide them by 12 and take the remainder, and you find those three remainders in this chart, and then the Q that you calculate from Q equals 2X minus P, which the formula I stated before for calculating Q, your Q must have this remainder if X, D, and P have these three remainders. Otherwise, it's guaranteed to not be prime. And this chart can also be used to increase or to decrease the search time in an RSA brute force attack by approximately 83%, because well, I'll go back to that slide. So RSA 2048 can be factored into two numbers, which they have to multiply to be 5 mod 12. And so they're either that midpoint X is either gonna have 3 mod 12 or 9 mod 12. And so it reduces, and so 2 out of the 12 possible remainders modulo 12 gives you approximately 16.6% of the numbers that you have to search to brute force attack RSA. And so therefore, as X grows large, so does the number of primes in between X over 2 and X, and therefore the probability of at least one successful Q increases as X increases. And more research is needed to establish a definitive proof of my conjecture, but the computational results are promising. And I guess I'll open the floor to any questions. Yes, sir.
You gave a definition of sexy primes, but I didn't hear the definition of twin or cousin primes.
Okay, twin primes are primes that are separated by a distance of 2. Cousin primes are separated by 4. And then sexy are separated by 6. And then I don't know what 8 and 10 and 12, and because it can be any even number up to infinity, or some subset of infinity, you know. But they can be any even number. But the most common ones are twin, cousin, and sexy. It just happened to be my football number was surrounded by sexy primes. And it was just kind of random, you know. Any other questions? Yes. Or no? Go ahead.
Are there any other real-world applications that you found that this theorem could be useful for?
The only thing that I can think of, like, thus far is just RSA, is somehow trying to reinforce RSA and trying to, well, I mean, it can be used to find new primes, because, you know, if you know all the primes to the left and you leapfrog over, you're guaranteed to find a prime on the right, according to my conjecture. And so but you have to check all the Q's to be for primality. So you have to have some sort of prime checking algorithm to check them all for prime. And then, but so, you know, you can find new larger primes, but the only application I can think of so far in my limited experience in the math world is just trying to crack RSA.
You have a break.
Dr. Vada, you had a question?
Goldbach or Bertrand Postulate, they are about at least 2, right?
Yeah, Goldbach.
Your series for at least 4.
Why
Why is that?
Goldbach's conjecture, says that every even number greater than or equal to, two, greater than two, every even number greater than two can be written as the sum of two primes.
Okay, and your conjecture is for?
My conjecture is that
Even
Bertrand's postulate can be used, for any x greater than or equal to 4.
Why is that difference?
Because where x is the midpoint is 4, so you have, so 3 and 5 are the first pair of equidistant primes, because 3 is the first prime in between in the first Bertrand frame. So the first Bertrand frame is 2 and 4, between 2 and 4, and then so you have 3 in that frame, and so x is in the 4 equals x equals 4 is in the middle, and then 5 would be the prime that 3 finds on the other side of 4.
Thank you.
Let's thank the speaker.